at surface area. I like to think about surface area in terms of a painter. So if you go to the store and buy paint, they will actually tell you how much area that tin of paint will cover. So if you wanted to paint something like your letterbox and you were wondering whether you had enough paint, you could calculate the surface area and then see how much paint you had in the tin and figure out whether that was enough. Now, the first thing we're going to look at is surface area of spheres. If we flatten the world, so the world's generally or almost a sphere shape, and if we flatten the world, we end up with these 4 little sections. And it turns out that the surface area formula for a sphere is 4 lots of a regular circle, the regular area of a circle formula, which is interesting. So I like to think about this map of the world over here as each of those 4 bits kind of coming together to make their own little perfect circle, and that's how the surface area formula is created. So with this first example here, we know that our radius is 3. So when I put that radius value in, 3 squared would be 9 times 4 is 36 pi. Now that would be our exact answer, and our approximate answer would be 113.10, and I've got to remember my units, so meters squared. For this one here, it's a little bit different. I can't just for surface area go, oh, that's a hemisphere, so I'm just going to halve the formula, because I've got this bit on top as well. So what I'm going to do is say that the surface area is going to be 4 pi r squared. We are going to halve that, and then I'm going to add the area of a circle onto that to account for this top bit. If I simplify that, this turns into 2 pi r squared, and then we've got another pi r squared. So I end up with 3 pi r squared, and my r is 5. So 3 pi times 5 squared, which is going to give me 75 pi meters squared for my exact answer, or 235.62 meters squared for my approximate. Next, we're going to look at the surface area of a cone. So if I flatten out this cone, I end up with pi r squared, which is the first bit of our formula, and then I end up with this curvy bit, and we can figure out the area of that by saying pi times the radius times the slant height. So the slant height is this bit here, which is 10 centimeters. It's not this. This is just the regular height. So I've got everything I need. So for this particular example, I can go ahead and put in my 6 for my radius and my 10 for my slant height, and I'll end up with 36 pi plus 60 pi, which is 96 pi for my exact answer, centimeters squared, or 301.59 centimeters squared for my approximate. And I should draw these curvy lines approximately equal to. Okay, sometimes when we're looking at cones, we don't have, or we're not given this slant height directly. So you can see here that that 9 is actually this length here. So what I'm going to do, or what I need to do, is employ Pythagoras. And hopefully, because you're working at well above the expected standard, you've seen Pythagoras before. If not, here's your introduction to it. So what Pythagoras says, what Pythagoras says is, if I have a right-angled triangle, I can label my 2 shorter side lengths A and B, and if I square those and add them together, that is the same as or equal to C squared, or my longer side, my hypotenuse. So I'm going to go ahead and substitute my values into this formula over here so I can find my S. So A is 4 squared plus 9 squared equals C squared, 16 plus 81. see. So I probably should have explained this too. To get rid of that square, what we've done is taken the square root of both sides, and then these cancel, and I end up with C equals the square root of 97. And in this case, I'm going to go ahead and find out what the square root of 97 approximately is, and we'll round that to 4 decimal places so we're more accurate in our final answer. Okay, so now I've figured out this bit over here. I'm going to come back and use this as my S. So S is this value and our R is 4. And now I can put those values directly into my formula. So pi times 4 times, am I going to fit it in? 9.8489. So my final answer for this is 174.03 centimeters squared. I've linked this down here as well. This is a really good video for a composite solid that involves a cone and a sphere. And also it uses this Pythagoras' theorem. So if you need to, or if you'd like to go and look at that, you can. The last example we're going to go through is for this composite solid, which is similar to question 6 in the exercise that you'll be working through. So we need to think back to that painter. He doesn't actually need to paint that whole rectangular prism because part of it's covered by that half cylinder on top. So let's think through what he needs to paint. And I'm going to draw a net of the bottom, or of that bottom rectangular prism. So the surface area is going to be equal to, firstly we've got this bit here, so 2.5 times 1.6, and I don't need to add the top bit of that because, as I said, it's covered by that half cylindrical shape. But then I do need to add on two side bits, so here and here. So 2 lots of 2.5 times 0.9. And I do need to add on 2 of these bits, the back and the front. So plus 2 times 1.6 times 0.9. Okay, so I've thought about this bottom bit. Now I need to think about the top bit. So I'm just going to write up here the surface area for a cylinder is this formula here. We only really need half a cylinder, and we don't need to worry about this top surface here either, because that's joined to the bottom shape. So bottom solid. So what we're going to do now is halve this formula, so I can take away those 2's, and I'm going to think about what my R is. My radius is going to be half of this length here. So my R is going to be 0.8, and my height is going to be this length here. So height is 2.5. Let's add that to our formula. So I've got plus pi times 0.8 times 2.5 plus pi times 0.8. Oh, sorry. Pi times, 0.8 squared. And when I put that into my calculator, I'm going to get the final answer of 21.68 millimeters squared.